Well, it's our pleasure to have Kieth here to talk about the A-12 and give you some facts about it. Like he and I were just talking, there's a lot of stories outside, some true, most of them are not. But anyway, he should be able to set you straight. Let me give you a little bit of background about Kieth. He's got a BS in Aerospace Engineering from the University of Oklahoma in 1960, an MS and PhD Aerospace Engineering at the University of Colorado 1992 to 1966. And in his work history, he was with Martin Company up in Denver on missile ground systems design and analysis, advanced programs, missile and space system research. Then he went to work for General Dynamics and Lockheed Martin in the Space Systems Project Office from 1967 to 69. And then advanced aircraft project engineer, air-to-air and air-to-surface conceptual design studies. And he was the chief of advanced designs. He was the director of series of studies leading to the A-12 program, Deputy Director of Systems Engineering, A-12, Director of Advanced Technologies, Stealth Technologies, and then Chief Engineer of Joint and Advanced Strike Fighter, the JAS program, leading to the preliminary configuration definition of the Joint Strike Fighter, the F-35. He retired after down select to two contractors, Lockheed and Boeing, for the F-35 prototype competitions in 1997. After that, he decided to do some part-time work after retiring. He worked with Space Launch Corporation, Scale Composites, which is Burt Rutan's company, and others on the concept for reusable air-breathing first-stage vehicle for launching small satellites. He also worked with Northrop Grumman, the old Westinghouse division, on various aircraft-related projects. He worked part-time with General Dynamics and Boeing legal teams on the A-12 termination lawsuit, 91 through early 2014. His current hobby is research on physics and economics of global warming, or climate change, or what it is now being called. He has super wife Pam, children Stephanie, Becky, and Doug, and a granddaughter Olivia, which is 5. Which is that, please welcome Kieth Jackson and his story on the A-12.
Thank you, Buster. Can everybody hear me? When Buster called me up to give this presentation, I said, oh yeah, I can talk about the A-12. I've talked about it a lot. And then I got to thinking a little bit more, and I noticed that all of my charts, graphs, notes, everything had been confiscated either by security or by the lawyers when the program was terminated. And the last presentation I gave on this was in August of 1991. Which was 22 plus years ago. So with my fading memory, I hope you will hold me to all the facts I give you tonight. But I did have one presentation that I gave at an AIAA meeting in Los Angeles in 1991, and that was vetted very, very, very carefully by the Navy lawyers. They didn't want me to give it, but the Navy technical people said it was fine, so I did give it, and that's going to be kind of the basis of what I'm going to talk about tonight. I didn't know exactly what to cover, so I thought I'd try to cover very, very briefly kind of the whole genesis of the airplane, a little bit about the aftermath of the program, and then if you've got questions, I can try to answer questions as much as I could possibly remember. First, I thought I'd just mention a little bit about the early A-12 history and stealth programs in general. We worked at General Dynamics, and in the early 1970s, early to mid 1970s, stealth was becoming something of interest. Unfortunately, we missed out on that. Our Washington office got a solicitation from DARPA for people who were interested in designing a stealth prototype demonstrator airplane. Our Washington office rep had been working with DARPA on missiles, and he thought it went to the missile division, so he sent it to the missile division. They said, that's an airplane, we're not interested in airplanes, and they rejected the offer to go work on it. So we missed out on that early stealth thing. But then in the mid to late 1970s, there were a series of aircraft concept design studies. First one was done on the Air-to-Surface Technology Integration and Evaluation Study at the Air Force Flight Dynamics Lab. And what they were doing there was, for the next generation of air-to-ground airplanes, they wanted to try to determine what were the new technologies that were really going to make that possible, what was going to help that. We did a series of studies of all kinds of airplanes. We didn't want to try to give the airplanes numbers because nobody could remember the numbers, so we gave them nicknames. One of the nicknames was Sneaky Pete. That was the stealthy airplane. I'll get that back in a minute. Well, I can show it to you. We had gotten interested in stealth after that first solicitation that we missed. I had been kind of an airplane buff, and I had known that the Germans, right at the end of World War II, had developed a flying wing, and it looked to me like that would be kind of an ideal thing for stealth. Didn't have vertical tails, all very smooth surfaces and so forth. So we put together a little 1/4 scale model of something that was kind of along the lines of the Horton, the German design. Put it out in our radar cross-section range that we had out in the backyard at the plant there. And when we got the data in, we were kind of amazed at how low a radar cross-section we had. I can very well remember in a meeting with Jim Morandi, one of our radar guys, we told him what the radar cross-section we've got. We're projecting to full scale, and he says, you got to be smoking opium. There's no way you can make the radar cross-section of an airplane that small. So that encouraged us a little bit. And yeah, we looked at all these different airplane designs, and one of the ones that did generate the most interest was the Sneaky Pete design. There were others that we looked at, vertical takeoff and landing, variable sweep, and so forth. That study came and went, and then we did a study called 1995 Aircraft Technology. That was an air-to-air airplane. We didn't really look at stealth as being that critical to air-to-air, but the Sneaky Pete as well as some supersonic designs were things that we looked at in there. Air Force got quite interested in it. In fact, there was a group in the Air Force, mostly in the black world, that thought that this kind of an airplane, a subsonic flying wing, would be best for the air-to-air role. And there were some reasons I can touch on later. We didn't internally think it would probably sell at the Air Force because it didn't have an afterburner and high thrust to weight ratio. But there was a significant controversy on it. I remember the guys in the Air Force had me go talk to the head of the Tactical Air Command. I think it was Mike Lowe at the time, although I maybe have the wrong director. And they presented this airplane as a possible air-to-air airplane would substitute for the F-22. And I think he said something on the order, over my dead body. So it was definitely not an air-to-air airplane as far as the Air Force was concerned. We've already looked at that. A little later, the Navy became interested in A-6 replacement. And that was in the early mid-1980s. Secretary of the Navy, John Lehman, was an A-6BN. He flew in the reserves, flew in the right seat of an A-6. He wanted an A-6 upgrade initially, but a lot of the people that had been briefed into the stealth technology felt like that the Navy really needed a stealth airplane. After a long series of internal meetings and discussions, they did decide that they wanted a stealth airplane, and after we had been working with a bunch of people in the Navy and the Air Force, they decided that there were only two companies that were really qualified for the stealth part of it. One was General Dynamics, and one was, quote, a West Coast company, who we didn't know who it was at the time. It did turn out to be Northrop because of their work on the B-2, which was highly classified, and we really didn't know anything about it at that time. So, at any rate, Lehman decided that he wanted to team two companies up on each team. He wanted a stealth technology company, which was General Dynamics in our case, and he wanted a carrier suitability company, so he told us to team with MacAir. And Northrop teamed with Grumman. Internally, the Navy and Secretary Lehman sold what became the A-12 as a baby B-2. They said, B-2's out there, there's been a lot of development work. It's going to be really easy to develop this airplane, so we don't need to do a prototype or anything like that. We just need to go in directly into an FSD design at that stage. So we did a study, and they did some radar cross-section tests and did down select, and we won the contest. Several people told me it was really kind of a hands-down win on our part. So that was encouraging. Now when we start right here on the Navy airplane, by the time we got to the program, it was, the A-12 was supposed to, supposed to replace the F-111 and the A-6. F-111 in the air-to-ground attack role, and the A-6, of course, the Navy carrier-suitable airplane. The 3 view of the airplane, most of you have probably seen it. 1,317 square foot wing area, 2 GE F-412 engines, which were kind of an uprated version of the F-404 that was used in the F-18. Pretty good sized airplane, 70-foot wingspan. Just to show you a few things, whoops, I keep punching the wrong buttons here. Radar antenna here and in here, electro-optical antenna, IR search track set there, flush-mounted antennas all over the airplane, leading edge devices for high lift on a Navy landing. We got yaw control with a spoiler and an elevon on the trailing edge. Did a lot of wind tunnel tests, a lot of simulator work on it, and we're sure it would fly fine. And of course, the B-2 proved that it could fly. The thing that really got us into it was aircraft survivability. Of course, we were doing this in the 1970s, and in particular, threat missiles were increasing a bunch. Typically, up until about the mid-70s, if a fighter particularly saw a missile coming in time, he could outmaneuver it. But the new missiles coming out had enough turn capability and a short enough time constant that they could basically outmaneuver any airplane that any pilot could survive. You just couldn't take enough G's to outmaneuver the missiles. Monopulse seekers made them a lot more resistant to jam, or a lot more vulnerable, less vulnerable to jamming. And also the missiles were good at hitting airplanes up to Mach 3 and over. They were effective at all aspects. They had look down, shoot down capability. So the missiles were getting pretty tough to defeat. A lot of the classical performance parameters looked like that they were not really going to be enough to justify a new airplane. Particularly in terms of a lot of the classical performance parameters like speed and so forth. Another issue that was coming to the fore, and it's probably even more relevant today, is cost growth. The historical cost for military aircraft just almost doubled or tripled each generation as we tried to get more and more performance, more speed, more altitude, higher dynamic pressures, and so forth. And so the technology explosion meant that we could put more performance into an airplane. If we tried to get it all, then we could pay for. So we really need to look at what we could leave out in an airplane to make it affordable. So it was a real trade-off in basically setting requirements. How fast do you need to have it? How much payload? What kind of range? And so forth. We did a bunch of studies. This was one that was actually for payload, but there were a lot of others in terms of if we've got a fixed amount of money for the whole fleet of airplanes, and then we want to get the most performance out of the fleet, not just the individual airplane. And you could see that as you, say for example, increase the payload along this axis, as you got more and more payload, the airplane got heavier and bigger, obviously. The individual aircraft effectiveness, as your payload increased, got better. You get more targets killed per sortie. Talk about that a little bit more later. But for a fixed budget, you couldn't buy as many airplanes. And we found typically as we went through that, you got a pretty well-defined peak. So there was a best size airplane, a best performance airplane. And you could go through a lot of the design variables and get this same kind of thing. How much stealth did you need? How much speed did you need? What kind of takeoff and landing performance did you need? Looked at in pretty much a total force structure context. And in terms of low observables, when we first got into it, we found out, gosh, we can get the radar cross-section down a lot further than we ever thought we could, and that's going to be pretty neat. We could take those radar cross-section reductions, and a lot of the radars that were out there, we could basically beat them. You know, they couldn't detect the airplane. And so we got pretty enthusiastic about it for a while. And then we started doing some reactive threat studies. They said, well, that sounds good right now, but what if the threats make the radars more powerful, or they go to IR search track sets, or they get better AWACSs or whatever. And we discovered that in the long run, no aircraft could be invisible. You're always going to get detected at some point in time, given the threat developments that went along with your airplane. And so we got a little less enthusiastic about it as time went on. And then as we got further into it, we discovered that low observables had a lot of very favorable interactions with other technologies. As far as the design of the airplane and the tactics the airplane could use, it turned out to be a lot more powerful even than we thought at first. And the key point there was that your survivability is not just not being detected, it's actually surviving an encounter, and there are a whole lot of steps a threat has to go through to kill you as you're coming in. The overall loss probability, if you take, for example, an air interceptor coming after you, he's got to be detected by usually an EWGCI set. He's got to be able to vector the threat to you, given detection, and so forth and so on. And it's a chain of probabilities. Our first thought was to try to avoid detection where you wouldn't have any problem. But assuming that you couldn't do that, there are all these other things in the chain. And for example, go back again, speed could help against a lot of these things to a greater or lesser extent. Keep punching the wrong button. But a lot of it was not that important. There were a lot of other aircraft design characteristics that would help some, not help some. If you took reduced observables, it was helping all the way across the board, except in things like hardening and a few other areas. And so putting the low observable technology into the mix gave us a much more powerful airplane than just the low observables themselves. Just as an example, if you take a radar cross-section, sigma 0, and you decide that you've got to penetrate a SAM belt, and this was the time when we were still looking at stopping a Russian attack across Eastern Europe, when there were thick SAMs all along the border. And if you looked at how many SAMs they had, you were getting painted on a typical airplane by, say, 3 different SAMs as you went through. And you looked at how much radar cross-section you needed reduction just to get through at random, any random place. This is 10 dB, that's a factor of 10, that's a factor of 100, that's a factor of 1,000, that's a factor of 10,000. You were not going to get there just with stealth alone. But then you looked at the situation if you knew where the SAM sites were. If you had an EWGCI system or a threat warning system that could tell you where the holes were, then you could get through with a much more reasonable reduction in the signature. Rather than 10,000 reduction, it could be between 10 and 100 reduction in radar cross-section. So to summarize, the low observables were a very powerful contributor to survivability because it impacted so many of the elements of an engagement. But we had to have other kinds of features, only with other things. Sensors were important to see where the threats were. We had to have weapons to kill the guys before they got to us. Countermeasures were still important, and by the way, the low observables really helped countermeasures a bunch because you didn't have to have as big a countermeasure, whether it was a chaff or a flare or whatever. And we needed, I'll call it compatible levels of speed and maneuverability. Situation awareness was one of the most important things. And it was certainly important in its own right. You need to be able to see the other guy before he saw you. That meant you made it harder for him to see you and made it easier for you to see him first. Multispectral sensors were important. RF threat warning and surveillance, accurate surveillance and track capability on the airplane was important. You want to be passive most of the time because he could see your radar if your radar was turned on all the time. So infrared search while track set was important. Infrared missile warning. The infrared missiles at that time period were getting most of the air-to-air losses on both sides. The first generation all-aspect IR missiles were just coming in. I think the AIM-9L, they were getting very lethal and very scary. If your radar, you didn't want to have a regular radar. You needed to have something that the other guy had a hard time seeing. So low probability of intercept radars were important. And just the old all-around vision canopy was also important. And then you needed to be able to fuse all that together, sensor fusion. Two-man crew helped. F-35, by the way, has taken this a long ways, and that's an extremely important area. Speed was one of the big issues that we had, and this was probably the most emotional single subject that we got into. All the fighter pilots had been taught since World War I that speed is life. And in fact, speed is always better, everything else being equal. The problem we had was for supersonic capability, everything else couldn't be equal. And in fact, your IR signature increased. And in particular, as you got up above Mach 1, it increased very rapidly. I remember we did some tests basically in conjunction with some Israeli requests. They were having trouble with foxbats down along the Suez Canal. They wanted a missile that could shoot a foxbat. And we worked with Pomona. They wanted to put an IR seeker on a large Standard missile. And so they flew some F-111s down along the East Coast at Mach 2.5 to see if they could get a lock on with that relatively small IR seeker. And they were locking on that IR seeker at close to 100 nautical miles. I mean, it was really eye-watering. Just a small IR seeker. That airplane flying at Mach 2.5 was really hot, and you could see it a long ways. The problem with the IR missiles, too, is they don't have a radar that you can see. You can't tell when you're being painted by it. So supersonic capability offered, that kind of a problem. It was more difficult to shape a supersonic airplane for low radar cross-section, particularly from the beam and the aft aspects. Internal volume was a lot more costly because it blew your wave drag up to have a big, high cross-sectional area on the airplane. The target acquisition became more difficult just with speed, particularly if you were going after a non-pre-briefed ground target. If you were going in at Mach 1.2 on the deck, it was almost impossible to see a non-pre-briefed target before you overran it. And then another thing that we found was that real supersonic performance was very much dominated by fuel consumption. Particularly as you started going supersonic, afterburners blew your fuel out the tailpipe in a big hurry. And in fact, we found, for example, that on most missions, the A-12 could actually have a faster average penetration speed than the supersonic F-18 because the F-18 would run so low on fuel, he had to cut way back to keep from running out of fuel. And while the F-111 could keep the power up and actually have a faster average penetration speed, even though it was subsonic. So we came to the conclusion that high subsonic speed was the best compromise. And that was for the air-to-surface mission optimization. Air-to-air total optimization could be a very different thing. The second issue was afterburners. All pilots like to have more thrust, and the afterburner gives you a bunch more thrust. And the airplane would be a whole lot more fun to fly with an afterburner, just like a very powerful car. It's kind of a blast to fly. But we found that infrared signatures, the IR missiles at that stage had been causing the great majority of air combat losses. And we decided that an optimized blend of reduced IR signature and countermeasures, flares and other kinds of countermeasures were the best solution. For the afterburner, we actually came to the conclusion, for various reasons, that putting an afterburner on the airplane would actually degrade the survivability, particularly because, wrong button again. It increased the radar cross-section in particular, even when the afterburner wasn't in use. And the main problem there was that very high afterburner temperatures were not compatible with the kind of materials we had, at least at that time, for radar cross-section reduction. And an afterburner also had very high IR signatures from an IR search track set, another passive device. At night, it lit up the sky when you turned the afterburner on. So we decided that we'd leave an afterburner off and we'd try to optimize the maneuverability of the airplane for dry power. One other very interesting thing, they'd been doing some flight tests out in the desert in a program called Aim-Val, Ace-Val, where they were trying to trade off new missiles and aircraft tactics. Going against the new all-aspect IR missiles, I talked to some of the F-16 pilots who'd been flying in that. They said the most important rule they had was never turn your afterburner on with high all-aspect IR missiles around. That if you came across a guy that was armed with an all-aspect missile, your best tactic was to chop it to idle power and go down into the ground background to give him clutter in the background. But afterburners were a definite no-no, particularly when you couldn't tell where all the threats were in a chaotic environment. Because even though you could see a guy and maybe work your afterburner for one guy, it was the other guy off to your shoulder that would get you. So we wanted to optimize maneuverability and dry power. Okay, so overall then, the rest of the things, hardening, make the airplane more survivable, and give you the right kind of weapon suite to be able to stand off from intense point defenses and suppress threat defenses. Looking at the other side of the story, lethality. The lethality was derived from good intelligence, accurate navigation, appropriate target acquisition sensors, low probability of intercept radars, for example, and FLIRs. Large payload remained very important. For most of history, it took multiple sorties to knock out a target. People would fly over and drop a bunch of bombs, and you had to have a whole squadron to knock out a target. As we were coming up with guided weapons, you could independently target about as many weapons you wanted to in a given area and have them all go in at the same time with GPS guided weapons. So you could look at actually getting multiple kills per target. And it actually made big payloads more important rather than less as you went to guided weapons. Internal payloads were best because you could go in and stay stealthy without the radar cross-section of your weapons. And you could also go in stealthy, suppress the defenses, and then as the defenses got beat down, it was useful to have external weapons. So you needed both internal and external weapons. Range was extremely important. That's one of the reasons, payload and range are one of the reasons the B-52 has been around for 60 years or so. You can put a lot of stuff in it and go a long ways, carry large payloads. For the Navy in particular, as the threats were getting worse, they wanted to stand off further from shore to stand off from the enemy missiles coming in. A longer range airplane helped them to do that. It reduced the tanker burden. For example, in the Afghanistan situation, their whole sortie rate was limited by tanker capability and not by the capability of the airplane itself. And so the A-12 turned out to have quite a long payload, which we designed into it, and which would basically make the whole fleet a whole lot more effective with large range. Reliability and maintainability were very important, so we worked hard to put that in there. And then for an airplane to be useful for a long time, large internal volumes were very important, range and endurance important. We needed an architecture for the avionics that could grow, and we needed to have growth capability in our power and cooling systems on the airplane so that when new stuff came along, you could put it into the airplane quickly. Talk about specific Navy requirements. The bring back payload, they didn't usually worry about that with the old dumb bombs, because if you came back with bombs, you just dropped them in the ocean and landed without the bombs. But if you got expensive guided weapons on the airplane, you need to bring them back. And the A-12 had more than twice the bring back payload of the current airplanes they had operating in the fleet at that time. A little bit about the specific configuration. We had a simple planform, no vertical tails, buried engines. The structure was very efficient. And in fact, some aspects of this got us into a little trouble later, but the weight of the main bending material in the structure to carry the bending loads in the wing, which are always important, is determined by the structural span over the thickness. And this had a very low, because it had a very thick wing. The B prime over T was low, which made it very efficient structurally. The planform gave us an aerodynamic center and the center of gravity that were right close together, which meant that you weren't limited by payload location. You basically could put fuel and weapons right basically on the payload. It had very high volumetric efficiency. Large internal volumes in a low wetted area meant that your aerodynamic drag could be kept low. Particularly for a Navy airplane where they've got a very limited amount of space on the deck, packaging efficiency was very important. And so basically the whole airplane, in terms of inside the wing fold, you'd fold the wings up on the deck, and this was the airplane that you had on the deck. Big main weapons bays, landing gear bay, outboard missile bay, weapons bays, nose weapons gear bays. So there really was very little acreage on the airplane that wasn't actually useful. And as a result, this airplane, which had more internal volume, payload, and so forth, was actually relatively small in terms of spot factor. It was actually smaller than the A6 it replaced, even though it had considerably better range, payload, and performance. In terms of planform constraints, this airplane didn't have a horizontal tail or a vertical tail. We didn't want an airplane that would pitch up. Without a horizontal tail, it would be likely to kind of go ass over tea kettle if you didn't do that right. And you didn't want to have it too stable because you couldn't get up to the maximum angle of attack that you wanted. So it really had to be kind of along this line of sweep back and aspect ratio where it was stable but not too stable. And so a lot of the planform was picked from basic aerodynamic stability reasons. In terms of aerodynamic efficiency, in terms of just a generic plot, parameter span over a wetted area is kind of an efficiency parameter, and maximum subsonic lift to drag ratio. Lift to drag ratio, basically, your range, your cruise range is basically proportional to your maximum lift to drag ratio. The A-12 was efficient enough, so typical fighters tended to have lift to drag ratios of, say, from maybe 8 to 14 or 15. A-12 was up here with the B-52s and the commercial transports. As a matter of fact, it actually turned out to be kind of up at the top of that point. So two advantages: better range, and you could make hard turns without a lot of power. So it was good if you got caught into a turning contest with an enemy fighter without having a great deal of thrust. So that high lift to drag ratio was important. Okay, that gives you a little bit of an idea about about what led to the airplane. I was going to talk a little bit about the termination and the legal aftermath. And by the way, if anybody's got any questions, I'd be happy to try to answer them if I can. One of the reasons that we got behind on the schedule, a lot of that was weight growth. Another thing that we had problems with was composite fabrication, particularly with some of the big ribs, stuff that the factory had never done before. And so those schedule delays in getting weight out and getting the manufacturing technology caused us to get behind on schedule. Another thing that was extremely important was the collapse of communism. Berlin Wall fell in 1989, which is kind of about the middle of the FSD program. The defense budget started going to a death spiral about that time. The program was designed to be a fixed cost development program, a fixed price development program, which was in effect a no-no. As a matter of fact, DOD had rules against that because development programs are notorious in not being able to accurately predict cost and schedule. But the company felt confident enough that if it did overrun some, that they would have the financial resources between McDonnell Douglas and General Dynamics that they could absorb it. But then both McDonnell Douglas and General Dynamics saw the out-year defense budgets cratering. They said, oh, wait a minute, if we get behind now, it's going to be a whole lot harder to make sure that I can fund it without going bankrupt. And so there were, at the end of in 1990, there were a lot of discussions between the Navy and the Air Force and DOD about how the program might be restructured to keep the airplane going. We had a critical design review in November of 1990, where the Navy gave thumbs up on the program, and then Cheney terminated it in January of 1991, just a month or so later. The Navy still said they wanted it, but the Navy then didn't have any money, and they said, well, if it's going to be terminated, I'm going to terminate it for default because I can't afford to pay what I owe the contractors. And that led to a legal fight, and that legal fight lasted 23 plus years. And so I think we probably paid, I don't know the numbers, probably $1 billion worth of lawyers' fees on both sides. Lawyers loved it. They just as soon keep it going forever. And it finally, after bouncing back and forth between the judge and the appeals court on several occasions, it finally got to the Supreme Court. The Supreme Court made great noises of disgust that it even gotten that far and sent it back and said, you guys just settle it. And although the government lawyers didn't want to settle it, by that time the contractors decided they didn't want it hanging over their head, so they did decide to settle it just this year. And I think the settlement was that the contractors, I think General Dynamics gave the Navy a deck house on a destroyer, and the McDonnell Douglas gave them a couple of F-18s and called it quits. So it was basically a tie at the end, which in any honest study, you probably should have been able to determine that in 6 months at the outside, but with lawyers it took you 23 years to get it settled. So anyhow, I've spent a significant amount of my time on that over the last 20 some odd years. But just to kind of give you how the airplane actually was stacking up when it was terminated, in terms of schedule, we had planned initially, to have a first flight about 5.5 years after the initial start of the contract exploration phase. When the program was terminated, we thought it would probably be about 7 years, so we were probably looking at a 1.5-year slip. The AX, which at that time, the time this chart was put together, the AX was supposed to be a replacement for the A-12. After what we learned, they decided they'd put the schedule out at 9.5 years. The B-2, we found, we didn't know this when we went into it either, had about 11-year schedule from that point. ATF, or the F-22, was around 12 years. In terms of development costs, we had a contract to do the FSD program. I think as I remember, the ceiling cost beyond which the contractors had to supply all the money was about $4.8 billion. We had spent or contracted for about $4 billion. We figured that we could probably get it done for less than $6 billion. The Navy, in their most pessimistic estimates, were that we could probably get it done for $7.5 billion. It ultimately happened that the Navy got the F-18EF, which was supposed to be just a minor modification of the F-18CD. They said they could do it for about $3 billion, so they could replace it as an interim before they got their next airplane. The last numbers I saw were that the actual F-18EF program was just about right there. just that minor airframe change, and they had some avionics developments later on that added to that. The AX, they were saying somewhere between 9 and 12 billion, 13 billion. The F-22 at the time I put the chart together was about 13 billion. I think it finally got up to about 20 billion before they were through with it. B-2 was out here probably pushing 30 billion. These are in then-year dollars. So the actual costs involved with the A-12 program were much less than the other competing airplanes at the time. In terms of technical status at termination, we had successfully passed the critical design review in November of 1990. We had over 99% of the drawings released, about 88% of the production tools were complete or available. About half the parts for aircraft 1 and 2 were available. Software for aircraft 1 was complete and in test. We had 8 engines running, and most of the major subsystems were in test. We had weight growth was about 6,000 pounds at termination, a little less than 6,000. I think actually, as I remember, it was about 5,600. The Navy evaluated that the performance would be acceptable with an additional 2,000 pounds of growth, which it looked like we didn't think we would get even very close to that. And I think at that stage the Navy didn't think that either. So that's why we passed the critical design review. In terms of aircraft performance, when we got the contract signed, oh, come on. Yeah. When we got the contract signed, the FSD, if you compared the aircraft performance to either the FSD specification or the NAVAIR estimate of what we would be at the end of FSD, which was a little bit less than the specification, design mission radius was almost 20% better than what the spec was. The maximum speed was about 5% better. Sustained G was right on what the NAVAIR estimate said it would be. Specific excess power was 10% better than what we promised. And the launch single engine rate of climb, recovery single engine rate of climb, and launch wind over deck were 5 to 10 knots better than what the specification was. And in fact, what we'd done was we had some initial conservatism in the design, and we'd had design improvements in other areas, particularly aerodynamics and some of the other propulsion performance areas. So all in all, the airplane actually looked quite good at termination from a technical standpoint. So that's a very quick overview of how the airplane got there and what happened to get the program terminated. I had put this chart together in 1991. It's been over 20 years since then, but I thought it would be worthwhile kind of summarizing where we actually are now. The world was pretty well unsettled at that stage. It still is. At that time, sophisticated weapons were proliferating to the third world. As the Soviet Union collapsed, that probably slowed down some, but it's picking up again with the Chinese. Overseas American bases were dwindling, and that has happened and has continued to happen. So in terms of power projection, we're getting more and more reliant on aircraft carriers, surprisingly. And the carriers and the long-range tactical aircraft at that time, and I think still now, continue to be best power projection tools. For example, the A-12, if we had it in Afghanistan, could have spent several hours unrefueled, loitering, providing air cover. F-18s had to have a number of refuelings and could only stay overhead for a few minutes. So those carriers and the ability to project power are still important. I mentioned that the A6 was still obsolete, still aging, and it needed to be replaced. It was replacement, not by the AX, but by the F-18 EF. And now I think the F-35C will finally begin to pretty much match in some respects, but not in others, the performance of the A-12. But that's been over 20 years later and a whole lot more bucks. So at any rate, it was a fun program to work on. I see some familiar faces here. I know a lot of you guys contributed to it. We learned a lot from it. I think we'd had problems with composite manufacturing and construction on the A-12. Those problems were pretty well solved by the time we got to the F-35, so that's been a whole lot smoother. The engines were actually used in the F-18EF and some other classified programs, and some of the radar technology is used elsewhere and so forth. So the technology has been used. That's too bad for all of us that worked on it that the airplane didn't go, but it was quite an experience. I personally started working on the design of Sneaky Pete back in 1975. And I just quit working on the legal aspects of it this year. So it's been a long, long time for me. Have any questions? It varied. In about the early 2000s, the main trial came up in front of the judge. Most of the time, I was actually conferring with lawyers, and I would come in and maybe confer a day or two a month. Sometimes before a trial, I would spend quite a bit of time. I spent one full day in front of the judge with lawyers trying to bait me into saying something stupid, which I guess I didn't get it too stupid, because that was the first time the judge says, "You guys are just fishing, get out of here." And that time he found for the contractors. But that was not the last time that we went through that. So, and then since then, I would guess that it's been tailing off for the last few years. I'd spend maybe, a total of 2 or 3 weeks a year, or maybe a little bit more than that, basically talking to lawyers and giving them background on the history. And when the Navy had some objections, I could talk about that. One of the things that I remember was that the first thing that the Navy tried to do to prove that the airplane wasn't any good. They hired some recently retired engineers from Northrop, from Pratt & Whitney, a couple of places to prove that the design wouldn't work. One of the Grumman guys, they had a guy from Grumman that said the structure would fail. And we got, luckily, some of our guys had kept a finite element model, and we gave that to a Boeing engineer, who was a consultant, and he found out that when the Navy guys analyzed the airplane, they had put only a few concentrated loads on the airplane to give the bending and torque loads, and all of the areas where they said the structure was no good was where the load introductions were. And it was just totally bogus. They had some Northrop propulsion guys said our propulsion system wouldn't work. I later found out that Boeing had some things that could be considered serious problems. They went to the trouble of building a large-scale model with internal engines in it to blow air through our propulsion system. Turned out it worked just exactly like we predicted it would, and just worked just fine. So after a while, the Navy and the lawyers decided that wouldn't work, and they eventually, everybody agreed that the airplane was fine. Everybody liked the airplane at the end of the program. So it was not an airplane problem. It was a contract problem that caused the program to fail. Yeah.
Why was the airplane canceled?
It was canceled because I'll give you the real reason, and I'll give you an excuse. The real reason was because the defense budget was going down. They had 3 airplanes in development, the B-2, the F-22, and the A-12. They couldn't afford them all. And the Navy, somebody in the Navy, I'm not sure who it was, felt that some Navy admiral had lied to him about the status of the A-12 program. He was ticked off. He was also in the process of just going to war in the Gulf. And he just decided right off the bat that he was going to terminate the A-12 program. He had to do one or the other, and he terminated the A-12 program. Legally, all the federal acquisition regulations said they couldn't do that. They had a whole list of things that they had to go through to prove that the airplane, there was no better, that there were better options to do the same job. They didn't go through any of that. Our termination letter, Cheney decided to terminate the program on Friday evening. The letter had to go out on Monday morning. so that they didn't have to put more money into the program at that time. They called a Navy lawyer up to write the termination letter over the weekend. She had no idea what the problems were. So she got another termination letter that they'd had earlier for the Navy P2 program, prop-driven, turboprop-driven anti-submarine warfare airplane. So a lot of the reasons that they gave for terminating the program, that we didn't even have any requirements. I think one of them had to do with propellers. We didn't have a propeller on the airplane. I mean, it was just obviously absurd, but that's the way the government works. Yeah.
Have you ever seen any estimates of the actual cost of the legal battle and how those numbers compare to what it would have cost to finish some of the first airplanes? It's a sad statement on the...
I have not gotten those. I've had some idea from the contractor side. I tried to make my own guess, and I may be way off on this, but I would guess it's probably around $1 billion worth of lawyers' fees. And I think we could have flown the airplane easily for half that, a lot less than half that.
It's a rather sad statement on the affairs of things when you consider all the folks that lost in livelihood.
Absolutely. It was a travesty as far as I'm concerned, but I am prejudiced, I'll have to admit.
How long would it have taken after termination to produce the first aircraft?
I think it would have taken, there were several different estimates. My own guess would have been, it would have probably taken a little less than a year. That's kind of where I came from. Yeah.
You have any thoughts on the pictures that are showing up in Aviation Week of the delta-shaped object that's been flying over Texas?
They're intriguing pictures. I tried to measure the planform, and it's got about a 45-degree sweep, which is what the A-12 had. It also had a straight trailing edge, which is what the A-12 had. I have no idea what it is or what it is. The Air Force, some Air Force spokesman said it was a B-2, and that it was an optical illusion that didn't have the jagged trailing edge. But those pictures look like a straight trailing edge, and the wing sweep didn't look right for a B-2, so I don't know what it is. Yeah.
Did you ever get a single airplane? Curious as to what the operational weight would have been for the jet engine.
We did not get an airplane into the air. We were probably about a year or so from first flight. The dry thrust of the engines were in the 15,000 pound thrust category with two of them. So, something in the order of 30,000 pounds thrust. As I remember, I can't give you an exact number on it this late date. The airplane was in about the takeoff gross weight, operational would probably 60, 70,000 pounds in that category. So it was not a high thrust to weight ratio airplane, particularly with all the stores and fuel on board.
And could it be configured for multiple missions like attack and air-to-air fighter missions?
Yes, it could. In fact, in some respects, it made sense as an air-to-air airplane, particularly from the Navy standpoint. It would carry 12 AMRAAMs, full-up AMRAAMs. I think the F-22 probably carries 4 internally. You may correct me on that. I can't be exact on that right now, but a lot more air-to-air missiles because of the large payload. They were talking about going to folding fin compact carriage AMRAAMs and AIM-9s. It could carry a pot full of those. It had a long loiter time out quite a ways away from the carrier, and in conjunction with E-2, early warning airplane, you could put a lot of them out there that were hard to see for bombers coming in. And a single airplane with 12 AMRAAMs on it could do a lot of damage to an incoming attacking force would go that far. Again, very high maneuverability and mill power when you didn't want to turn your afterburner on for fear of IR missiles. It would not make a good deck launch interceptor because it did not have the high burst speed. but it made a very, very good missileer, which is a concept that actually does make some good sense, I think.
Yes, back in the day, I remember seeing some pictures of the A-12 configured as a refueler tanker,
Yes.
and it was also configured to replace the Navy's AWACS.
Yes. Yeah, there are a couple of points on that. Those huge weapons bays, you could put, and we had designed fuel tanks we could put in the main weapons bays. It would carry a lot of extra fuel, so it made a really good tanker. We had designed it so that we could have put a third man in the crew station fairly easily. And with a large acreage on the leading edge of the wings, you could make a pretty good early warning aircraft. One of the things I meant to mention, the radar was kind of interesting. I always make the analogy. We had the radars on each wing leading edge. Those radars could see from across each one of them could get to front 30 degrees or so, and then they could look out behind your wing line. And if you think about predators, you know, owls or eagles or lions or tigers or cats or dogs or whatever, they've got their eyes looking forward, and the rabbits and the prey animals have all their eyes out to the side, rabbits and squirrels and so forth. The A-12 had both. And with all that acreage on the leading edge, you could get a pretty much light dimming radar capability in it. Not many. As a matter of fact, right now, they're shipping truckloads of classified documents out to be burned. They confiscated everything on the program. There are some things that have been unclassified, mostly the lower classification things. But a lot of it, particularly a lot of the more sensitive technologies, are still classified and probably will remain so. And I couldn't tell you point by point exactly what is classified and what's not, so I tried to stay away from classified stuff tonight.
What did they do with all the tooling and all were developed yet?
They basically got rid of them, sold them off, junked them. So there's really not much left. There are a few parts around. You know, the mock-up is out at the museum out there, but basically they're all gone, as far as I know. Yeah.
How many people lost their jobs when that program was terminated? And what happened to that building out there? Is Lockheed using it now?
Lockheed used it for quite a while. I think that they have now decided the employment's going down enough so they're not using it now, the last I heard. Overall the country, somebody added up about 20,000 people all over the country were laid off that day. I've actually been on airplanes and struck up a conversation with a guy next to me who lived in Florida, and he lost his job that day on the A-12, a little company that worked in Florida. So there were lots of people all over the country that lost their jobs. It was a black day for a lot of us.
Is it true, the black hole out at General Dynamics, they removed all the Doritos out of the vending machines?
That's probably true. Yeah.
It's interesting because you were mentioning about the tools and leftover. This thing doesn't work very well. Some of the ribs and stuff that you were mentioning surfaced a few months ago. There was a big old crates of that stuff going to salvage.
Is that right? There was a flap a few years ago where somehow or other one of the canopies McDonnell Douglas got sold to a secondhand shop. Some of those canopies had some very classified treatments on them. The thing came up for, I think on eBay or something like that, and a guy that had bought it for something like $50 was trying to sell it on eBay for $20,000, some ridiculous amount of money. I can't tell you the exact thing. And there was a big flap about what it was. I think it turned out not to be one of the ones with the secret technology on it, but.
There were piles of that stuff out in Weatherford at the surplus shops.
Is that right? Yeah, I didn't know that. Yeah.
I can work this thing. On one of your earlier slides, you had said that a lot of the technology was already known. Did that technology, was any of that dependent on transfers from the government from like the B-2 program?
We got basically nothing from the B-2 program. Northrop had basically had the B-2 just about in flying shape when this program started, and there was basically no technology cross-fertilization. So when the government, the Air Force and the Navy sold to their leaders that it was a no problem development program, they were thinking in terms of Northrop, because everybody thought Northrop would win because they had the B-2. Unfortunately, their design was not nearly as good as ours was. And so we really got very little, if any, technology transfer from them. We had done a lot of work ourselves, though, kind of a lot of it on a shoestring. But we, for example, did win the full-scale model test-off on the radar cross-section, as well as better range and payload and that sort of thing.
Do you have any words to say about the contract we had? It was a 50-50 split. It wasn't a 49-51. It was a 50-50 split with Mac Air. Was that a concern?
That was one of John Lehman's bright ideas. What he wanted to do, and they basically dictated this to us, he wanted to have two fully qualified airframe companies teamed up on the development. And then he wanted to split the two companies apart and have us compete with each other on production, and kind of mandated a 50-50 split. It turned out, and he did that because he thought it would be cheaper. He'd keep competition in the program. The problem is you can't have 1 year where you get 2/3 of the airplanes, and the next year you only get 1/3. You got to lay off a lot of your people, and then it's almost impossible to get them put together again later. So what we had done was to try to get a factory in Tulsa, Oklahoma, the old Rockwell factory that we could both basically run, and we could basically shift people and stuff back and forth. We basically have different management for the competition. I mean, it was a crazy idea, but anyhow, that's what we had to work with.
What was the production cost per aircraft, and about how many aircraft were anticipated to be sold?
I don't remember the exact number. I'll give you what was kind of off the top of my head. It was like $35 million, $35 to $40 million maybe, and I'm probably off on that a little bit. That was in 1992 or 1993 dollars, somewhere in there.
And about how many aircraft were anticipated to be sold?
That number changed, and I can't remember exactly where it was at the end of the program. I think at one time it was like 650, split between the Air Force and the Navy. I think that had probably gone down some toward the end of the program, but I can't give you exact numbers at the end of the program.
Do you have any information on the status of the F-23?
Of which?
The F?
No, I don't know what the status of that is. No, I don't know. I don't know anything about that. Anybody else got any questions?
I take it they never intended to have guns on that thing.
Never intended to have guns on it. It was a missile carrier. We'd actually looked at putting a gun in it, but the Navy decided they didn't want it.
They did with the F-4 too.
Yeah, true. Okay, well, thanks for bearing with me.